Do 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 do. Hey guys, today's topic is probably the most important topic of the entire semester, and it's too bad that I can't be here in person to teach you because I don't know, I get excited about it, and I'm sure you guys can feel my excitement through the screen. But I get really excited about this, and it's got a great name because a lot of mathematicians get excited about it. This is called the fundamental theorem of calculus. And mathematicians only use the word fundamental for very, very, very important theorems. And I'm going to write it out first, and then we'll see if we can dissect what it means and why it's true. And this gets used to find the exact, and this is no longer approximate, area under a curve. So it's going to turn out that all that work you've been doing the last 2 days was meaningless because it's easier. This is why it's so important, the fundamental part. It's easier to find the exact area in most cases. I shouldn't say that most, but most cases that we are going to run across. Obviously, there are all sorts of crazy functions out there that maybe we can't find the exact area of. But for the functions that we're going to come across, it's easier to find the exact area. And that's very counterintuitive, and at the same time talks about the beauty of math. So that's nice. So let's write it down. Let's write down the fundamental theorem. This says the area under the curve of f prime of x. That's an important part here. The area under the curve of f prime of x from x1 to x2 is given by f evaluated at x2 minus f evaluated at x1. I'll write a capital A here. This is a true equality. So you'll notice it's the derivative up here. Derivative there, and these are not derivatives. In other words, so another way we can write this using antiderivatives we have that the area under the curve of f of x from x1 to x2 is given by a. We can now talk about this as an integral of f, and then we use this is interesting notation, we use a vertical bar and we say x2, that means evaluate at x2, minus the integral evaluated at x1. So the vertical bar means evaluated at. So that's another way we can write this. Other times you'll see it written as capital F of x2 minus capital F of x1, where capital F of x equals the antiderivative. There are lots of ways of writing it. But they're all saying the same thing. It says that you can find the exact area under a curve using antiderivatives. And this is really, I mean, this is the layman's version of the fundamental theorem, is this last line. You can find the exact area under a curve using antiderivatives. And it's really a fascinating concept. I'll give you a quick intuition as to why, but a lot of you probably don't care too much. I care, so that's why I'm going to give you the quick intuition. So let's go back. Let's take a step back. We approximated area using rectangles. And if we look at our formula, and I'm just going to use the left endpoint formula. This was x2 minus x1 divided by n, f of x1 plus f of x1 plus x2 minus x1 divided by n plus dot 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 plus this last piece. That was our left endpoint version. And if we look at this and then take n to infinity, right, we make, in some sense, this means extremely small in width. Extremely small width vertical rectangles. All of a sudden, you know, when we're calculating the area of something, just give myself a curve here. The area that we're calculating is, we're doing these really tiny vertical rectangles. We're adding up pieces like this. And all of a sudden, we get closer and closer to the actual area if you do infinitely many of these vertical rectangles. Now I'm making myself sad that I've made myself such a wide piece. It's going to take me a little while to fill this in with vertical lines. But you can think about these lines actually as really tiny rectangles, and if I get infinitely many of them, then I get the area exactly. I use infinitely many vertical lines to fill in the area. And add up each of their areas. I get the exact area under the curve. And so that's the whole idea here, is that we're really taking, you can use the midpoint rule or the right endpoint rule, or really any of the point rules if you want, because when these strips get infinitely small, they all turn into each other. But I'm going to use the left endpoint rule, and as long as you add things up correctly, what it ends up looking like is an antiderivative. And the real reason why does the above look like an antiderivative is, take for a moment, let's just call this area, call this point X, and call the entire area A of X. And then we're going to add a tiny little piece of width H. So then the new area would be A of X plus H. So just think about it like that. If I look at A of X plus H minus A of X, then that is the piece I'm going to shade it in red. Shaded in red. So that's the piece shaded in red. I'm going to give my curve the name f of x still. The piece shaded in red has a height as a rectangle. It has a width of h. And it has a height of f of x. You could call it f of x plus h. You could call it some midpoint too. But the idea is we're going to push h really small. I can rewrite this whole piece by dividing by h. I can rewrite the whole thing as f of x equals a x plus h minus a of x divided by h. And now all of you guys, you better be able to see what's going on here. This, if h goes to 0, then it's a derivative. Or in other words, we certainly can push h to 0. There's no reason why we can't. So we push h to 0. F of x, which you'll remember is our curve, up top there, f of x is the curve. So the curve is actually equal to the derivative of this area function that we're talking about. And once we know that the curve is equal to the derivative, then we know that the area function, a of x, is equal to the antiderivative. It has to be. But now we to a certain extent we want to know how a of x relates to the antiderivative if we were to evaluate at specific points. Let's look at that instead. So the area is equal to the antiderivative, but that's assuming we've started really at x 1 there on the left. And so that's where we really get that it's equal to the antiderivative evaluated at x2, really at x. This is a area from, it's evaluated at x here, and then you subtract off f evaluated at x1. And so that's just so your plus c makes sense, right? Because otherwise you would have this plus c sitting around, and then you could technically say that you have any amount of area because you could choose whatever you want for c, and that's not true. So you technically have to choose some starting point. Choose some starting point x1. You choose that starting point, and that's this x1 here. So that's just so that you can't get, you know, as much area as you want. This is what sits around to make things work. Okay, so that's kind of the idea, but like, you know, how do we actually use this? Well, we have a better notation than what I used above. So the better notation is called the definite integral. And this is just an integral with bounds. So we put an x1 at the bottom and an x2 on top. F of x dx. This equals the area under f of x from x1 to x2. And is evaluated by capital F of x2 minus capital F of x1, where capital F of x prime equals f. That's, you know, that's another word for saying you find your antiderivative and then you plug in the endpoints. I'll put that in quotation marks because this is what you want to remember. Find the antiderivative. And in this case, plus c doesn't matter anymore. I'll show you why in a bit. You find the antiderivative, plus c doesn't matter, and then evaluate it at the upper endpoint. Then subtract it evaluated at the lower endpoint. This is the heuristic you want to follow. It's just this thing in quotation marks. If you're looking for the exact area under a curve, you find the antiderivative and then evaluate it at the upper endpoint, then subtract it evaluated at the lower endpoint. This is what the fundamental theorem of calculus says. So let's just evaluate some definite integrals first, and then we'll take some word problems where it asks us to find areas. So let's just find a couple examples. 1 to 3 of x squared minus x dx. Let's do -3 to 4 of, let's do the square root of x plus 1 dx. Oh, I can't do -3 there. Be square root of a negative number. -1. -1 to 4, the square root of x plus 1 dx. All right. So the top one, there's a 1 and a 3 sitting around, but in some sense we just want to forget about it. By and large, this is an antiderivative. So to take an antiderivative of x squared, we use our power rule, and that says I'm going from x squared to x to the 2 plus 1 divided by 2 plus 1 minus, and then x is really 1 plus 1 divided by 1 plus 1. And then we use this same notation that I used earlier, the vertical bar 1 to 3 means evaluate at 3 minus evaluate at 1. So that's the notation we like to use. And okay, so really what's going on there? This is really x cubed over 3 minus x squared over 2 from 1 to 3. And so what is this actually equal to? I plug in 3 first, right? Evaluate at 3. 3 cubed over 3 minus 3 squared over 2. This is really me plugging in 3. And then I subtract, I plug in 1. 1 cubed over 3 minus 1 squared over 2. And this is pretty important to put your parentheses around each piece, because then you remember to distribute your minus signs if you need to. That's the world's ugliest one. Plug in 1. So what does this look like? Well, that's 27 thirds. That's 9 minus 9 halves minus 1/3 plus 1/2. And so a -9 halves plus 1/2 is really -8 halves. That's -4. This is 5 minus 1/3. And 5 minus 1/3 will be 14 thirds. So we get an answer of 14 thirds. That's how to do one possible definite integral. Just going to separate these out so we don't get confused as to which one is which. And then we'll do another definite integral. This is the the square root of x plus 1 version. And to a certain extent, you guys are going to say I should use u substitution here, and I agree with you, but I'm also smart enough to know that using u substitution would not change my problem whatsoever. And by that I mean you can just use the power rule on this piece as is, because the coefficient on x is 1, so the derivative of the inside is 1, and in that sense we already have everything we need to just use the power rule. Go ahead and use u substitution if what I said doesn't make sense to you, because it probably won't. And then you'll see exactly why it does work when you do it. But basically you can just use the power rule on expressions like this as well. So this is x plus 1 to the 1/2 plus 1 divided by 1/2 plus 1, evaluated at -1 and 4. So I can rewrite that as, this is really 3 halves on the bottom or 2/3 on top. X plus 1 to the 3 halves, evaluated at -1 and 4. Or in other words, plug 4 in. So if I plug 4 in, I get 2/3 times 5 to the 3 halves minus 2/3 times 0 to the 3 halves. This is me plugging 4 in, and I subtract plugging 1 in. So that's how all of these are going to turn out. I'll rewrite this finally. This is 2/3 5 to the 3/2. And this seems like just a crazy number, but this is going to indeed be the areas of curves. Right now we're just calling them definite integrals. But it turns out they're the same thing. So there's an example of two definite integrals, and the notation we like to use that vertical bar notation. So just keep in mind the vertical bar notation. If I write f of x vertical bar x1 x2, this is f of x2 minus f of x1. So it's just something we'll see all over the place, so keep it in mind. All right, now let's tackle a problem of areas. Find the exact area under the curve f of x equals e to the 2x minus x cubed from x equals -1 to x equals 2. Man, I'm really bad at writing ones. I should just do the vertical stroke ones instead, but too late. Okay, so now we want to interpret this. This is just one step. This is a one-step transition to a definite integral problem. And the one step is the fundamental theorem of calculus. So you say by the fundamental theorem of calculus, the area, the exact area that it's looking for, the area is equal to the integral from -1 to 2, this is a definite integral now, of our function, e to the 2x minus x cubed dx. And we can use u substitution on e to the 2x, or I will help you guys out here as an aside. And I'll throw this on your exam too. The integral, the indefinite integral of e to the ax dx equals 1 divided by a e to the ax plus c. And you just get there by use substitution. That's all it is. So we're going to use that. So if the a in this case, what's playing the role of a is the 2. That's right there. The 2 is playing the role of a. So the indefinite integral here is 1 over a, but 2 is playing the role of a. So 1 over 2 e to the 2x minus, and then we use the power rule on x. So this is x to the 3 plus 1, which is 4. Divided by 3 plus 1, which is 4. And then, as always, we're going to evaluate at -1 and 2. And so we just plug both numbers in. 2 times 2 is 4, minus 4. 2 to the 4th power is 16. 16 over 4 is a big 4. And then, parentheses again, this is really 1/2 e to the -2 minus, now if I plug -1 in there, it's 1/4. So this doesn't really simplify great. You can simplify it if you want to be, I guess this is 1/2 e to the 4 minus e to the minus 2, and then we have a negative 4 plus 1/4, which is negative 15/4. So sure, that's the answer. Looks crazy, right? What is this actually calculating? I'll draw it on here for you. What in the world is this? Is the problem calculating? Let's draw my function e to the 2x minus x cubed. Looks something like e to the 2x by itself. Just draw this in another color. E to the 2x by itself looks something like this. Negative x cubed by itself looks something like this. So our actual function, when you add them together, you kind of are going to get something like this. It's probably going to bend like that, but then it's going to be pushed back up. So this is probably something like e to the 2x minus x cubed. So then what's the area that we're calculating? The area is from x equals negative 1 to 2. So that would be something like here. Negative 1 and 1, 2 would be like here. And it's absolutely fascinating that we can find this area. This area right here. We are able to find it exactly using antiderivatives. So we just found out that that area right there, even though it doesn't look like it, that area, this area A, is given by that crazy number up there. It's absolutely insane. But anyway, I hope you can see how this is a really exciting concept. That's all I'm going to do today. We'll go through more practice problems tomorrow. But it's really nice that you can calculate areas exactly by just taking an antiderivative and evaluating it at some endpoints. All right, have a good one. I'll see you all tomorrow.